All right, hello everyone. Wish your semester is going well and you stay healthy. Now let me take the lecture video for the 13th week of this spring semester. So now we're approaching the end of the semester. Just we are left with 2 more weeks. So I wish you keep up the steam and keep up the good work. I also do my best in the remaining 2 weeks to finish this lecture successfully. So this week, what I'm going to do, I'm going to talk about chapter 12, that is about constraint optimization. So in the previous week, we initiated our study of constraint optimization. We studied the main analytical tool for this kind of question, that is a so-called Lagrangian multiply method. And this method translates the constraint optimization into unconstrained optimization using this artificial variable, lambda, which we refer to as the Lagrangian multiplier. So in the live lecture last week, we studied how to construct Lagrangian from the given constraint problems and how to find the stationary points. So you may regard these stationary points as the candidates for the solution. Okay? So now we know how to identify candidates. The upcoming question is, how do we choose one solution among these candidates? Okay, so that's what we are going to study this week. So we are going to study several criteria. Using those, we can choose one solution where the function is maximized or minimized given this constraint. Okay, so more generally, we study how to find the solution to the constraint optimization problem. So I'm going to show you several methodologies. So several methods that can be employed to find the solution. In this first video, let me introduce the method that can be adopted whenever constraint is given by a bounded set. Okay. So let me first elaborate on what I mean by bounded set. Its definition is really simple and intuitive, so easy to understand. So in math, we say a set is bounded if it is a finite size. So more precisely, set B, if we have a set B, the set is bounded if for every element x in that set, there exist finite numbers b1 and b2 such that x lies in between these two finite numbers. Okay, so if every element x in that set lies between these two numbers, then we say set B is bounded. Okay, so every element is bounded below by some number, finite number b1, and bounded above by another finite number b2, then the set is bounded. Okay? So one standard example of a bounded set is the closed interval in the real numbers. So interval from a to b, that is a bounded interval because every element in this set is bounded below by a and bounded above by b. Okay, so bounded below and above by two finite numbers, so it is a bounded set. So there's not much I have to explain for this closed interval. But if we extend this notion to multivariable cases, so now we have a constraint involving two variables. So if we examine whether this is a bounded set or unbounded set, so first writing this as a set using the set notation. So collection of x1 and x2 such that 2x2 equals 60. And this is an unbounded set because if we think about the set of possible values for x1, x1 may go below negative 1 million or negative 1 trillion and so on, right? Because although x1 is a huge negative number, if we choose x2 accordingly, say in a huge positive number, there is a way to satisfy this equation. So there is a no lower bound and upper bound for x1 and x2. As a matter of fact, if we graph this linear equation, we are going to have a straight line on this x1 and x2 plane, and it goes on forever in both directions. So the set of possible values for x1 and x2 is unbounded. But if we impose one more condition on this set, so now two variables are non-negative, okay? Then the set becomes bounded. Okay? In this case, now the set is captured by line segment in the first quadrant. So in this set, the set of possible values for x1 lies between 0 and 15, and x2 lies between 0 and 30. So bounded below and above by finite numbers. So it is a bounded set. Okay, and then another example of a bounded set is a unit circle. Okay, x squared plus y squared is equal to 1. So in this case, two variables lie between -1 and 1, so it is a bounded set. But if we change the sign in the middle to negative, then it becomes a unbounded. Okay? All right, so now using this notion, we are going to study the first method. With that, we can find a solution to constraint optimization. But we have seen a simple version of this method in chapter 9. So the basic idea of this method comes from closed interval method, which is studied in chapter 9. So to remind you of this method, we studied how to find the global max or mean of a single variable function if the function is continuous and defined on closed and bounded interval, say from A to B. Okay? So we just talked about the notion of boundedness, just briefly mentioning about closedness. We say set is closed if the set contains the all boundary points. Okay? So this interval has two boundary points A and B, and this interval includes all boundary points, so it is a closed set. Okay? And if the set is closed and bounded, we say the set is compact. Okay? So the compact means two things, closed and bounded. Okay? So whenever function is continuous and defined on a compact set, say compact interval, we can make sure the function attains a global max and global min. Right? So here is one example. We have one continuous function defined on closed interval from -1 to 5, so on compact interval. So it has a global max and global min over this interval. And then the way to find the global max and min, we first find the stationary point of this function. The function has two stationary points at 0 and 3 in this example. And then we evaluate the function at these 2 points. And because the extreme value may occur at boundary points, so we have to evaluate the function at this left-hand point and at the right-hand point. So we have a total of 4 points, okay? And then we choose the largest one, okay? So the largest value is 25. So the function attains a global max at this point. So at the right-hand point, 0.5. Okay? And then we choose the smallest one. So smallest value is a -27. So the function attains global mean at 0.3. That is a stationary point of this function. Okay? So one advantage of this closed interval method is we don't have to examine the sign of the second derivative. So we don't have to adopt the second derivative test. So without the aid of the second derivative test, we can find out where the function takes the largest or smallest value. Okay? And furthermore, the same idea and same technique can be applied to multivariate cases, so multivariable cases. Okay? So specifically, if the objective function is continuous and the constraint set is bounded and closed, but whenever constraint is given by some equation or equality, is given by some equality, then it is automatically closed. So the set has all boundary points. So we don't have to worry about the closeness as long as the constraint is given by some equation. Okay. If the constraint is given by some inequality, then we have to think about the closeness. But whenever constraint is given by equality, if the constraint set is bounded, then it's going to be compact. Okay. So the function is continuous and defined on a compact set. Then function has a global max and global min. So as a result, optimization problem has a solution. Okay? So this is the so-called extreme value theorem. So it guarantees existence of global max and global min whenever a function is continuous and defined on compact set. Okay? So now we use this theorem to find out the solution. So global max or global min. So solution to this constraint optimization problem. So the procedure is pretty analogous to the closed interval method. So we have to first check whether the conditions are satisfied. So the function we want to maximize is continuous and the constraint set is bounded. So if these two conditions are met, we set up the Lagrangian to find all stationary points. Okay, so remember the way to construct the Lagrangian is L is a function of xy lambda. So we first put the function we want to maximize in front, and then plus lambda c minus g of x comma y. Okay. So in the constraint, we move the function g to the right-hand side. Okay, and then the expression on the right-hand side, put it in the bracket. Okay, so that is the way to construct the Lagrangian. And then find all stationary points of this function. Right? And then we evaluate not the Lagrangian, but the function we want to maximize at this stationary point. Because Lagrangian is just the auxiliary function we use for solving the optimization problem. That's not what we want to maximize. What we want to maximize is the function f. Okay? So after finding stationary point of this Lagrangian L, we have to evaluate the function f at that stationary point. Okay? And because the extreme value may occur boundary points, so we have to find the boundary points of the constraint and evaluate the function at those points. Okay? Then in the end, so the point where, so among these points, among the stationary points and boundary points, the points where the function f takes the largest value is going to be the solution to this maximization problem. And in case of a minimization problem, among these points, the point where the function takes the smallest value becomes the solution. Okay? So one advantage of this method is we can find out global max and global min at the same time. Okay, so we don't have to follow another procedure. So we don't have to. So we don't need any other procedure. Just by following this procedure, we can find out global max and global min simultaneously. Okay? And another advantage of this method is just like the closed interval method, we don't have to examine the second order condition. Just the Lagrangian multiplier method alone gives us the information about the global max and global min. Right? Now, let me show you several examples on this method. Okay, so this is possibly the simplest one. So the function is given by x times y, and the constraint is given by some line segment. Okay? And we assume two variables are non-negative. Okay? So we first check the objective function is continuous. So partial derivative of this function is well defined, meaning that this function is differentiable. So differentiability implies continuity, so the function is continuous. Okay? And then the constraint is a bounded set, because if we graph this function, x plus y equals 6, so we assume x and y are positive, non-negative, right? So that's going to be line segment in the first quadrant, just like in the previous example. So this is a bounded set. Okay? So the two conditions are mapped, so we can apply the previous method to find the global max and global min. Right? So let me start with the Lagrangian. Curly L is xy plus lambda times 6 minus x minus y. And then find the stationary point of this. So L sub x, L sub y, L sub lambda. Okay. So partial derivative of this Lagrangian with respect to x. So that is y minus lambda, and set it equal to 0. And partial derivative with respect to y, we obtain x minus lambda is equal to 0. And then L sub lambda, that gives us the constraint. So 6 minus x minus y equals lambda. All right? So the way to solve this equation, the system of equations, is a piece of cake, because each equation is really simple. So from the first equation, I can see that y is lambda. From the second, x equals lambda. So I can put in lambdas for x and y in the last equation. And the last equation comes down to 2 lambda is 6, so lambda is a 3. Okay? So we obtain the value of lambda. So the value of x and y are immediate from the first two equations. So the Lagrangian has a unique stationary point at 3, 3, 3. So from now on, let me denote the stationary point of Lagrangian by the x star and y star and lambda star. Okay. All right. So after finding the stationary point, we evaluate the function f at this point. So because lambda is just an artificial variable, so ruling out this lambda, we evaluate the function f at 3, 3. And function assumes value of 9 at this point. Okay, and then in the third step, we evaluate the function f at these two boundary points. So the boundary points of the constraint is a 6, 0. The coordinate of this point is a 6, 0. And the coordinate of this point is a 0, 6. And because the function is defined by the product of the two variables, so we can easily see that at these two boundary points, the function boils down to 0. All right, so now we are done. We can simply choose the largest value, that is number 9. So the function attains global max at this point, 3, 3. And the lowest value is a 0. So the function attains global mean at two distinct points at the two boundary points. So 0, 6 and 6, 0. Okay, so this is the way to find the max or mean. So how to find the solution to constraint optimization whenever constraint is given by a bounded set. Okay, so let me show you two more examples. So the second example is a little bit more challenging than the previous one. So now I translate the problem into utility maximization problem. So now the objective function is utility function. So considering x1 as a demand for good 1 and x2 demand for good 2, so this function U stands for one consumer's level of satisfaction. So in other words, the utility. Okay. And then the price of a good 1 is given by 20 cents, so 1 over 5. And the price of a good 2 is $1. And then the consumer has $4, so the budget constraint can be written this way. Okay, so total expenditure for consuming x1 amount of a good 1 and x2 amount of a good 2, or x2 units of a good 2, whatever. Okay, so total expenditure is equal to the consumer's disposable income. All right. So if we graph this linear equation on x1 and x2 plane, we're going to have a line segment as before. Okay, and each variable stands for demand, so intuitively it should be non-negative numbers. So the constraint becomes a line segment in the first quadrant. So that is a boundary set. If we identify the horizontal and vertical intercept, then horizontal intercept is 20 and the vertical intercept is 4. Okay. Then we start with the Lagrangian. L is 2 square root of x1 plus x2 and plus lambda multiplied by the constraint x1 minus x2. Right? And then for finding stationary points, we compute the partial derivative with respect to each variable. So L sub 1 indicates partial with respect to x1, L sub 2 with respect to x2, and with respect to the Lagrangian multiplier. Right, so L sub 1 is 1 over square root of x1 minus lambda over 5, and set it equal to 0. L sub 2, 1 minus lambda, L sub lambda, the constraint. Okay? And the way to solve this equation is, so let me first solve the second equation, because that is the simplest one. So from the second, I know lambda is equal to 1. Okay? And then substitute this value into the first equation. Then the first equation comes down to 1 over square root of x1 equals 1 over 5. Okay? So from that, I can obtain the value of x1, 25. Okay? And then substitute this 25 into the last equation. Then 4 minus 5 minus x2, that is 0. Okay? So from that, I can deduce. So I get to know the value of x2, that is negative 1. Okay? So I just found all entries of the stationary point. So Lagrangian has a unique stationary point in this example as well. And at the point 25, negative 1, and 1. All right. So after finding stationary point, if I think about the constraint and this stationary point, you know what? Constraint requires two variables be non-negative. Okay? But the stationary point tells me the second entry. So x2 takes a negative number. All right? In other words, this is a stationary point of the Lagrangian, but it does violate the constraint. Okay? So this is clearly not the candidate for the solution because it does not satisfy the given constraint. Okay? So we'll rule out this stationary point. Right? So we conclude that no stationary point satisfying this given constraint. for this Lagrangian function. Okay. All right. So sometimes, after finding the stationary point of the Lagrangian, you have to double check whether given constraint is satisfied at the stationary point. Okay. If it violates, then you have to rule it out from the candidates for the solution. Yeah. All right. So because there's a no meaningful stationary point, we can just check the boundary points of the constraint. So the coordinate of the boundary points, 20, 0. So 20, 0 and 0, 4. So at the right endpoint, the function u assumes 2 square root of 20, that is a square root of 80, and at 0, 4, so at the left hand point, the function u assumes 4, right? So 4 is a square root of 16, so clearly this one is the largest value, and 4 becomes the smallest value. Okay. So the solution to this maximization problem is 20, 0. So the function u has a global max at this point, so at the right hand point, given this constraint. If the problem was a minimization problem, then the solution is 0, 4. Okay. So whenever extreme value occurs at the boundary point, like in this example, in economics we say that objective function has a Kono solution. Okay. But if the solution is between these two boundary points, so some points on this line segment, then we say that objective function has a interior solution. Okay, so interior solution is an antonym of the Kono solution. Okay? So whenever Lagrangian has no stationary point, we have to suspect the possibility that maximum or minimum value occurs at the boundary points. Yeah. All right. So now let me do some little bit more challenging problems. So the little bit more challenging problem, that is this example. So we have x squared y, and the constraint is given by this one. This is the equation of ellipse. So if we graph this equation on xy plane, so the largest possible value of x is a square root of 1.5, and smallest possible value is a negative square root of 1.5. And for y, largest value is a square root of 3, and smallest value is negative square root of 3. Okay, so this is going to be ellipse with this ratio, and looks like this. And this is clearly bounded set, and the objective function is differentiable. Okay, so using the same method, let me compute the max and min of this optimization problem. So construct L. Okay, so and then we compute partial derivatives. So system of equations. So L sub x is that equal to 0, and L sub y and L sub lambda. So the reason why this example is a challenging than the previous ones is, the system of equations is a little bit complicated. And the problem is there's no standard way to solve this equation. This is not a linear equation, so we can adopt a linear algebra to solve this equation, right? So it depends on case by case. So for this equation, so for this system, let me first solve out the first one. Okay. So the first equation tells me 2xy minus 4x lambda. So I can see common factors here. So factoring out 2x, and we'll be left with y minus 2 lambda, and that is equal to 0. Okay. So the solution to this equation is either x is 0 or y is 2 lambda. Okay, so we have two possibilities. So now let me divide my analysis into two cases when x is equal to 0 and when y is equal to 2 lambda. Okay. So case 1, when x is equal to 0, okay, then the second equation comes down to 2 lambda y is equal to 0. Okay, and I have another two possibilities. So to satisfy this equation, lambda must be 0 or y must be 0. Okay, but if I think about the second solution, if y is equal to 0, because I already assumed x is 0, it means both x and y are equal to 0. But given constraint requires 2x squared plus y squared must be 3. Okay, but both x and y are equal to 0, then there's a no chance to satisfy this equation. So at this point, constraint is violated, so I can rule out this, this solution. Okay, so throwing away this solution, then I'm left with just this case. So when lambda is equal to 0, right? Then x is 0 and lambda is 0. And I have to find out, the remaining variable y. So, the last equation tells me y squared is just a 3 because x is 0, right? So y is either plus or minus square root of 3. Okay? So in the first case, I have two stationary points, 0, square root of 3, and 0, or 0, negative square root of 3, and 0. Okay? So the first number is for variable x, second for variable y, and the last one for Lagrangian multiplier lambda. Right? So this is what happens in the first case. So now we examine the second case when y is equal to 2 lambda. Case 2, and y equals 2 lambda. All right. So in this case, the second equation comes down to x squared is 4 lambda squared. All right. So putting these two, 2y for lambda and 4 lambda squared for x squared, in the last equation, I obtain 3 minus 8 lambda squared minus 4 lambda squared is equal to 0. So lambda squared is 1/4. So lambda is either 1/2 or negative 1/2. All right. Okay, so if lambda is 1/2, if lambda equals 1/2, then y should be 1, because y is a 2 lambda, and x must be 1. Okay. So I have one critical point here. Okay, and if lambda is -1/2, then y is going to be -1, and x is still 1. So I have this point, -1 and -1/2. Okay? So I can find out two another stationary points in this second case. All right, and then we evaluate the function x squared y at each stationary point. So at the first stationary point, the function assumes 0. At the second, also 0, because x is given by 0. And at this stationary point, the function assumes 1. And at this point, -1. All right, and then now we examine the boundary points. Okay, so at each boundary, so this constraint has 4 boundaries. So this point and this point, this point and this point. Okay, so it has 4 vertices or 4 boundary points, but each boundary point, so at each boundary point, either x or y is equal to 0. Okay, but the function is defined by the product. So we can see that at every boundary point, the function assumes 0. Right? So our conclusion is, so which one is the largest value? The largest value is number 1. Okay? So the function attains a global max at this point, 1, 1, and the global minimum at 1, -1. Okay? So this is the kind of the multivariate version of closed interval method. So without the aid of the second order test, so second order derivative, we can find out where the function takes the largest or smallest value whenever constraint is given by a bounded set. Right? I hope you found this video useful, and then I'll see you in the next video.